Once we have the definition of the derivative presented and practiced a couple derivatives using the definition of the derivative, and we've gone over some of the basic differentiation rules, we can apply this idea to rates of change. And a lot of times we want to use our applications of our derivatives with rates of change, such as rates of change of population, rates of change of cooling, and also just rates of change of position. And that last one is what this video is focusing on. So let's just think about some different ideas of this actual application of rates of change. So when we look at the movement of an object, especially starting maybe at like on the number line, if I'm looking at finding the average velocity of that object, I want to take the change in distance divided by the change in time. And we can think of this a lot even in our idea of driving. So if I looked at my watch before I started on a trip and I saw what time it was, and I looked at my odometer and I saw how many miles I've driven on that vehicle, and then I go for a drive for, say, an hour, and then I look at the difference in my odometer reading divided by the difference in my time, then that gives me my speed, and speed being the absolute value of velocity for that trip. So if I went, for example, 60 miles over that span of time of 1 hour, then that means my average speed is 60 miles per hour. Now, does that mean that I always went 60 miles per hour? No. I could have gone much slower than that in certain times of my trip and faster than that in other times in my trip, but my average velocity over that interval of time was 60 miles per hour. And oftentimes looking at the idea of the average velocity, then I have my change in distance, my displacement, divided by my change in time, when I can look at this in terms of velocity that has sign. So velocity usually is positive when the object is going up or when the object is going right, and then it's negative when the object is going down or when the object is going left. And certainly that is dependent on how you set up your coordinate system, but that is oftentimes the convention of how that works out. Now, when we look at the notation for this, a lot of situations, they actually use the name of your position function to be the function s, and your time being the independent variable t. So s of t is often what they have as notation that gives the position of that particle at any time t. Now, if I just put some definitions of some symbols that we're going to use, then if I say t sub 0 is my initial or my start time, and t sub f is my final time, then my average velocity is the position when I end. So run the final time through your position function to see when you ended. So that's like looking at the odometer after you finish your trip, minus the position evaluated at t sub 0, your start time. So that's subtracting off what the odometer reading was when you started your trip. So there's your change in distance divided by the t sub f, the final time, so that's what your watch said when you finished your trip, minus t sub 0, what your watch said when you began your trip. So again, we have our change in distance divided by our change in time to get our average velocity. And it's important to remember that average velocity is over a span of time. Now, what if we also we're interested in it, what is our instantaneous velocity? What is our velocity at any given time in the trip that we took for the speed, which again, speed is the absolute value of velocity. Or if I'm actually looking at the projectile or other particle in motion and I want to find out when it was going up or when it was coming down, so I want to preserve the sign of the velocity function. Well, my instantaneous velocity then would be taking this change of position divided by change in time. But instead of saying t sub final here, say it's t plus delta t. So my position function s of t plus delta t, so your beginning time plus a change in time, run that through your function, minus s of t, all divided by your t plus delta t minus t, but that simplifies to delta t in the denominator. And I want to do this as an instantaneous, not over a span of time. So I want to look at the limit as my change in time approaches 0 to get it where I have the instantaneous velocity instead of the actual average velocity. Well, that's what my velocity, instantaneous velocity function is equal to. And if you look at this and you remember back to the definition of the derivative, when I had a function named f of x notation and I had my dependent variable being x, then when we think back to that, we had our limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. That was the definition of our derivative of our function. And that derivative gave us the slope of the tangent to that function at any given value of x, whenever that limit exists. Well, notice here, this is exactly the same structure as the definition of the derivative. It's just that here my output function is s, where before our output function was f, and our independent variable here is t, where before our independent variable was x. So this actually just gives me the derivative of the function, and the function that this was applied to was the position function. So our instantaneous velocity function is equal to the derivative of the position function whenever that limit exists. And so when I'm asked to find an instantaneous velocity of a particle at any given time, and I know the position function, I take the derivative of the position function, and that's the instantaneous velocity function. And then I'll just evaluate that instantaneous velocity function at the time that they're asking about, and that will give me my instantaneous velocity at that time. If they ask me the average velocity, I don't use any calculus in that. The average velocity, we just take the change in position divided by the change in time to get the average velocity. So again, when you're kind of thinking back with just an analogy you can grab onto, thinking about that when we're driving our car and we are looking at the speed idea of it, my average speed is, if I did that, look at my watch when I start, look at my odometer when I start, drive my distance, then look at my watch when I stop, look at my odometer when I stop. So the odometer at the end reading minus the odometer at the beginning is my change in distance, and then my ending watch reading minus the original watch start time is my change in time. That would give me the average speed. But then, as I was going through that trip, if I just glanced at the speedometer right at that moment, that is my instantaneous. So you want to think about that in terms of when you're looking at these, and then apply it specifically to velocity that has sign and how you can keep those straight. Now, when we're looking at the idea of acceleration, when you think about changing your speed over a span of time, then that rate of change is the change of speed with respect to the change of time. So my instantaneous acceleration function is the derivative of the velocity. I want to just review the relationship between the position function, the velocity function, and the acceleration function, and then get started on some parts of an example. Here, if we have our position function is s of t, then to find the average velocity over a span of time is v sub avg, just for the abbreviation for average, is the position at the final time minus the position at the initial time divided by the final time minus the initial time. So I get my average velocity that way. If I'm looking at a question and I'm interested in finding the instantaneous velocity, that's when we apply the calculus to our position function and find that the instantaneous velocity function is equal to the derivative of the position function. And then I would just evaluate that instantaneous velocity function at the given time. For our instantaneous acceleration function, we denote that with a of t for the first letter of the word acceleration. And the acceleration is the derivative of the instantaneous velocity function, which then would have been the second derivative of the position function. So that's the relationship between them. So here I have the height of a projectile shot from ground level is given by the position function s of t is equal to negative 16t squared plus 256t. The first part says find the average velocity between t equal 1 and t equals 6. So since this is the average velocity, we're going to apply that formula to it. So my v sub average is s of my ending time 6 minus s of my beginning time 1. And I divide that by my ending time 6 minus my beginning time 1. So here my average velocity over that span of time, well, s of 6, if you take out the t's and put in 6 instead, you're going to get 960 minus s of 1, if you take out the t's and put in 1 instead, you get 240 divided by 6 minus 1 is 5. So I get that that is equal to 144 feet per second for that average velocity. Now notice the second part asks you to find the instantaneous velocity of that particle at t equal 2. So now since it's the instantaneous velocity, that's when we are looking at it as the limit as delta t approaches 0 of that change in distance divided by change in time. So we're taking the limit as the change in time approaches 0 to get at an instant, and that's when my velocity function is equal to the derivative of my position function. So look at this position function. It is two terms, and it is a constant times a letter base to a number power. So that's just the general power rule to differentiate. So bring the 2 down, multiply to negative 16. So that's negative 32t to the subtract 1 from the exponent. So that'd be the first power. And then plus the derivative of 256 times t is 256 times the derivative of t, but the derivative of t with respect to t is just 1. So 256 times 1 is 256. And then once I have that instantaneous velocity function, we're going to evaluate that instantaneous velocity function at the time that it's requesting 2. So you take out the t and put in 2 instead, and we have our negative 32 times 2 plus 256, and we get our v of 2 is equal to 192 feet per second. So that's an example that shows you the comparison between the average velocity type question and the instantaneous velocity type question. Let's look at a couple more types of things that they could ask us. and go through some more. So I've rewritten the original problem that we had, the same position function as the previous parts that we did, and just asking some other types of things. So here, the height of the projectile shot at ground level, again, I'm using that S of t is equal to negative 16t squared plus 256t. And the first part here says, find the time at which the particle hits its maximum height. Now remember, velocity has sign associated with it. Most of the time when we set up our coordinate system, when we have the particle going up, it has a positive velocity, and then when the particle starts to come down, it has a negative velocity. So right at that moment, when velocity transitions from positive to negative, that's that split second at which it hits its maximum height is when the instantaneous velocity is 0, and then it comes back down. So to find the time at which the particle hits its maximum height, we want to take the instantaneous velocity function and find out the value of t for which the output of the velocity function would be 0. So remember, our instantaneous velocity function v of t is the derivative of the position function. So that's negative 32t plus 256. So then it will hit its maximum height when the output of the velocity is 0. Solving for t, we're going to add 32t to both sides. Divide both sides by 32. We get t is equal to 8 seconds. So the time at which this particle will hit its maximum height for that given position function is 8 seconds. Now find the maximum height. Now to find the maximum height, I want to take the time at which it hit its maximum height and run that through the position function. So this first part, we found the time is 8 seconds. So we will have our position function evaluated at 8. It gives me negative 16 times 8 squared plus 256 times 8. And that gives me the position function evaluated at 8 seconds gives me 1,024 feet. So the maximum height of the projectile is 1,024 feet. We did an example where I gave you the position function. If we have a free-falling object and the only action on that object after it's released is the acceleration due to gravity, there's a form of the position function that is handy to know so that you can just go ahead and get your position function from that introductory information and then answer your questions from there. So if we're looking on the Earth's surface and it's a free-falling object, meaning there's no other action on it other than the acceleration due to gravity after it's released, and first of all, if you're measuring in feet and seconds, the position function will have the form S of t is equal to negative 16t squared plus v sub 0 is your initial velocity at which the object is thrown or shot off, times t, and then plus s of 0 is your initial position. So whether it was shot off from the ground level, your s sub 0 would be 0, or whether it was shot off from, say, 3 feet above the ground level, then your s of 0 would be 3, etc. Now, if you were measuring in meters and seconds, and this was still on the Earth's surface, then your S of t is going to be equal to negative 4.9 t squared plus your initial velocity times t plus your initial position. And this is all measured then, again, like I said, in meters per second. If you're on the moon's surface, then, and measuring in meters per second, your position function would be S of t is equal to negative 0.81 t squared plus your initial velocity times t plus your initial position. So each of them have that format. Now let's look at this next example. A projectile is shot 2 meters above the moon's surface, and it's meters and it's the moon's surface, so it's going to be this position function format that we're going to use, with an initial velocity of 3.24 meters per second. And the first one says find the position function. Well, we saw again that it's the moon's surface and measured in meters, so our position function s of t will be equal to negative 0.81 t squared plus my initial velocity. It says with an initial velocity of 3.24 meters per second. So I have 3.24, then t, and then plus my initial position. It shot 2 meters above the moon's surface, so that's plus 2. So there's our position function. Now it asks us to find next the instantaneous velocity at 1/2 of a second after it is shot off. So remember, instantaneous velocity function is the derivative of your position function. So my v of t is going to be equal to, we'll bring down the exponent, multiply that to the constant, so that's negative 1.62t plus the derivative of 3.24t is 3.24, and then plus the derivative of a constant term is 0. So there's my instantaneous velocity function, and I want to evaluate that at 1/2 of a second, taking out the t and putting in 0.5, so I have negative 1.62 times 0.5, and then plus the 3.24. Our instantaneous velocity at 1/2 a second after it is shot off is equal to 2.43 meters per second. The last part of this example, let's find the maximum height the object will attain. So again, remember that our velocity has sign. Positive when the object's going up, negative when the object's coming down. So at that instant where the velocity, instantaneous velocity is 0, that's the time at which the object hits its maximum height. So to answer, find the maximum height of the object will attain, we first want to find the time at which the instantaneous velocity is 0, and then run that time through the position function to see how high above, or what the position of that object was at that time. So our instantaneous velocity function for this problem is negative 1.62 t plus, and I've erased the rest of it, but it was plus the 3.24 t, so it'll be plus the 3.24. And then we want to know when the output of the velocity function is 0. So 0 is equal to negative 1.62 t plus 3.24. Add the 1.62 t to both sides, and divide both sides by 1.62. My t is equal to 2 seconds. That's the time at which it hits its maximum height. And then running that 2 seconds through the position function, we have s of 2 is equal to negative 0.81 times 2 squared plus 3.24 times 2, and then plus our position was 2 meters above the moon's surface when it was shot off, so that's plus 2 for the initial position. And when you run that through, you get that s of 2 is equal to 5.24 meters for its maximum height. Well, I hope this video was helpful to you in finding like the different connections between the position function, the average velocity, the instantaneous velocity function and the instantaneous acceleration function. For a review of the definition of the derivative, I've put the link to my video in the description of this video, and also just some links of other derivative rule videos that I've made in case you want to review those as well.